All right, good afternoon, everybody. Okay, so today we want to solve some questions on radioactivity. Okay, so the last in the last video we stated that our disintegration per seconds is given to be dn over dt is equal to lambda n, and because it is reducing as the rate of disintegration is going, it is decreasing with respect to time. We have our dn over dt, all right, is equal to minus lambda n. Your lambda is the k constant, then n is the final number of atoms. Then we also stated that our half-life T1 over 2 is given to be 0.693 over the decay constant. All right, so that is that. Then we said also that decay constant lambda is equal to, if you make use of the formula, is 0.693 divided by half-life. All right, we further stated that our final number of atoms is given to be n is equal to n naught, then inverse of ln, all right, raised to power minus lambda time taken. All right, so those were some of the things. This final number of atoms is equal to the initial number of atoms. This shift lane, inverse of lane, raised to power minus lambda t. Okay, then number 5. So I began to state, all right, some other formulas or supplementary formulas that can be used in calculating for radioactivity. So I talked about, for instance, if you are doing O-level examinations like maybe JAMB or like, you can easily use these other formulas. Okay, so I talked about first of all half-life. All right, you can use half-life as supplementary formula to be T half is equal to time taking over log 2R. All right, so now your R here is what we call disintegrating ratio. All right, so we can use this to calculate for T years time taking. We can use this value to calculate for half-life as well. Then number 6, I talked about the fact that your N is what we call the number of half-lives. All right, and there are two formulas for R, which is disintegrating ratio. The first formula is R is equal to final number of initial number of atoms over final number of atoms, or initial count rate over final count rate. Or we can also use R is equal to 2 raised to power number of half-lives. And number of half-life is time taken over half-life. All right. So this, if you are to determine number of half-lives, use what? Time taken divided by half-life. Then your disintegrating ratio is given to be initial number of atoms divided by final number of atoms, and that initial number of atoms is also called initial count rate, and this final number of atom n2, R is equal to n1 over n2. N2 is called the final count rate. Initial number of atoms or initial count rate, final number of atoms or final count rate. Then I said you can also use disintegrating ratio is equal to 2 raised to power the number of half-life. So those are the values you can use if you are to determine half-life, number of half-life, and disintegrating ratio. So the other value I talked about is fraction of atom that's decayed in the radioactivity. All right, because we state that it's actually radioactivity deals with the disintegration of an atom. So your fraction of atom that's decayed, all right, the value is given to be number of atoms is equivalent to R minus R1 over R. If you are to determine the fraction of atom that's decayed in the radioactivity, all right, multiply your final number of atoms, open bracket, disintegrating ratio minus 1 over disintegrating ratio. I've shown you already how to calculate for the values of disintegrating ratio using n1 over n2, or R is equal to 2 raised to power n. So note this thing. This is what we call half-life, this disintegration per seconds, this half-life, this decay constant, this the formula for the final number of atoms, this another supplementary formula for half-life, this is the number of half-lives, all right, number of half-lives. All right, to calculate for number of half-lives. This one is for disintegrating ratio, initial number of atoms. There are two formulas. The first one is initial number of atoms over final number of atoms, or initial count rate over final count rate. This n1 is called both count rate and atom and count rate. Then you can also use R is equal to 2 raised to power the number of half-lives, n there. All right, number of half-lives. So now if that is gotten, this one is fraction of atom that's decayed, which is number of atoms, open bracket, disintegrating ratio minus 1 over disintegrating ratio. So you can use that. Then number 7, we have fractions of, or let's say, okay, this one is supposed to be number of atoms that's decayed. Rather, sorry for that, number of atoms that's decayed. But your fraction of atom that's decayed is given to be R minus 1 over R. Okay, this one is number of atom that's decayed, while this one is fraction of atom that's decayed. So take note of your question if they ask it. Then the number 8 is what we call the fraction of atom remaining, FR. Fraction of atom remaining, FR, is given to be 1 over disintegrating ratio. All right. So number of atoms that's decayed in a radioactivity is given to be n open bracket r minus 1 over r. Fraction of atom that's decayed is given to be r minus 1 over r, while the fraction of atom remaining not decayed or remaining undecayed is given to be 1 over disintegrating ratio. So that is all of the values we are going to be using applied in this question. So let us take the first question right from this place. So the first question goes thus. They said after three half-lives, they did not say the half-life. They said after three half-lives. That means number of half-lives in that place is 3. All right, we are taking questions already. So we have questions. So they said after three half-lives. So the number of half-life is given to be 3. Okay, the question went further and said, you can write it down, comma, the fraction of a radioactive material that has decayed is dash. Fraction of atom that has decayed is unknown. So where is the formula for fraction of atom that has decayed? Fd is equal to r minus 1 over r. That is the formula you are going to be applying. So we are to determine the what fraction of atom that has decayed according to the question when number of half-life is given to be 3. What we're going to do is very easy. So the solution to that parameter, all right there, is now going to be Fd, if you recall it, fraction of atom that has decayed is given to be r minus 1 over r, disintegrating ratio minus 1 over disintegrating ratio. So fraction of atom that has decayed is equal to, we don't have r yet, but we are giving the number of half-lives. But don't forget that I said your r is equal to 2 raised to power n. So you are going to be applying r is equal to 2 raised to power n to calculate for the disintegrating ratio so that you can apply it here. So your disintegrating ratio is now going to be r is equal to, you have 2 here. What's the number of half-lives in the question? You have 3. That is 2 raised to power 3. Then your r is equal to 2 raised to power 3 will give you 8. Alright, that means r is equal to 8. Then you have fraction of atom that has decayed where r is equal to 8. So now be what? 8 minus 1 over 8. Then you have fraction of atom that has decayed to be 8 minus 1 will give you what? 7 over what? Over 8. This is the fraction of atom that's what decayed in the radioactivity. It's very simple. So you can apply all of those formulas to calculate for anything you are asked for. So if you have to calculate for fraction of atom remaining, all right, you can also do that. That's 1 over r. So next question, that's question number 1. All right, question 2. We solved like 3 questions on that manner. Okay, the question goes thus. A radioactive sample initially contains n atoms. All right, question 2. They said a radioactive sample initially contains n atoms. So we have the number of atoms to be n. All right, n atoms. Okay, so the next line, full stop, atoms, full stop. After 3 half-lives, they said after 3 half-lives, so the number of half-life is 3. Okay, the number of atoms that have disintegrated is dash. So we are looking for, here we calculated for fraction of atom that is disintegrated, but here is talking about the number of atoms that is disintegrated, which is Nd. Alright, Nd is here, number of atoms that's disintegrated according to the question. They said a radioactive sample initially contains n atoms, full stop. After 3 half-life, the number of atoms that have disintegrated is dash. So you are looking for Nd. So you have Nd is equal to, now what is the value for Nd? Nd is what? N open bracket r minus 1 over the value of r. Then you have number of atoms that's disintegrated to be, the value of n is going to be n. It was not going to be any particular value. So you have n into what? R. What is the value of r? Use what? R is equal to 2 raised to power. Don't forget that it's not only 2 raised to power n that can be used to calculate for the value of r. If you have 2 different count rates, 2 different number of atoms and 2 different count rates, you can use, alright, divide the first one by the second one, you still have the value of r. But because your n is given, which is supposed to be the number of half-lives, you are going to be applying 2 raised to power n and not r is equal to n1 over n2. So what is 2 raised to power n in this term? 2 raised to power n will give you 2 raised to power. The value of n is 3. So you have r is equal to 2 raised to power 3 will give you 8. So this n is equal to n, alright, into r minus 1. R minus 1 will give you 8 minus 1, then over 8. Alright, then what is number of atoms that's disintegrated? That is Nd is equal to, so you have n open bracket 8 minus 1 will give you 7 over 8. So n times 7, that is Nd, that is equal to 7n, alright, or n into 7, alright, everything over 8. So at the end you have number of atoms that's decayed is equal to 7n over what? Over 8. So that's what you're going to be having at the end of the day. So that's how to calculate for it. So in the same question, if I have to determine the fraction of atom that is remaining here, Fr, what are you going to do? Fr, fraction of atom remaining is 1 over r. So you have what? 1 over disintegrating ratio. Then you have Fr is equal to 1 over. What's your disintegrating ratio? R was calculated to be 8. So you have what? 1 over 8. The same applies to the first. So that is how to go about your calculations in radioactivity. Okay, so the next question, all right, we'll solve like three questions, like I said. Let's move like this. The next question says that a radioactive substance has a half-life. A radioactive substance has a half-life of 20 hours. Okay, so they said the half-life of the radioactive substance is 20 hours. So you are going to find somewhere to write out your parameters. Okay, now this one is one number of half-life. Number of half-life and half-life is different. All right, this one they said that the half-life of the radioactive substance is 20. Said a radioactive substance has a half-life. That means in a context, once we're talking about the number of half-life, it's talking about half-life. That's what T1/2. This question number 3. T1/2 is going to be 20 hours. So I've said before that the SI unit of your half-life is also the SI unit of your time taken. So half-life is going to be 20 hours. Then what's the next thing? Full stop. What fraction of the original radioactive nuclide will remain after 80 hours? So they are asking for the fraction of atom that will remain after 80 hours. So time taken is equal to, don't forget, I've said already that the SI unit of your time taken is the SI unit of your half-life. Half-life, time taken, vice versa. So except you are asked to further convert if you are doing advanced calculations on radioactivity. So if this is the case, I'm looking for the fraction of atom remaining, all right, and half-life was given, and what is it called, time taken is also given. So what's going to be the solution? What's going to be the solution here? I'm looking for FR, and the formula for FR is given to be 1/R, which is supposed to be the fraction of atom remaining, 1 over disintegrating ratio. So 1/R. How do I calculate for the value of R? Now I can't use R is equal to N1/N2 because I don't have initial and final number of atoms, neither do I have initial and final number of count rates. So I'm going to be applying R is equal to 2 raised to power N. Can I get the value of N? That can be gotten because I said that N is given to be time taken over half-life. All right, if that is the case, let me find N using this formula. So I have, if you make half-life result of formula here, because you can also use this formula to calculate for half-life. So you are going to be having half-life is equal to T over the number of half-life. So, but I don't want to dwell in that. I'm looking for N. So I'll just start from N is equal to T over T. This one is for when you're calculating for half-life. If you are looking for time taking, your time taking automatically becomes N multiplied by T. All right, you make it, that's the simple mathematics. You make your value insert of formula in terms of the other. So N is equal to T over T. So I have N is equal to, my value of T here, small letter T, is 80 divided by the value of half-life is 20. So I have N is equal to 0 cancel 0. So what is 8 divided by 2? 8 divided by 2 gives me what? 4. So if I have 4 as the value of N, now my formula is FR is equal to, final atom remaining is equal to 1 over disintegrating ratio. FR is equal to 1 over R. I have the value of N already to be 4. Then I'll apply R is equal to 2 raised to power 4. So that is FR is equal to 1 over 2 raised to power 4 will give me 16. So that means my fraction of atom that is remaining is what? 1 over 16. All right, 2 raised to power 4 is 16. Then I'll just apply 1 over 16 there. Because 1 over R is the formula, then you have 1 over 16. So that is basically how to calculate for half-life calculations in half-life. So I'll take one more question, all right, then we'll call it a day. That was a question that has a half-life and question that has a decay constant put together. Okay, so the next question I have in this place, the question goes thus. All right, we have, I want to pick a question on decay constant actually, so that we could solve a question or try a question that has a decay constant. So let's go with this. They said a radioactive element has a decay constant. A radioactive element has a decay constant. A radioactive element has a decay constant of 0.077 per second, because the SI unit of decay constant is in per seconds. So the decay constant lambda is given to be 0.077 per seconds. Okay, then let's move on. Calculate its half-life. It's very easy. We are coming back to this equation. All right, half-life is given to be what? 0.693 over lambda. So you just divide the value of what? 0.693 by this value, then you have your half-life. T half is equal to 0.693, all right, divided by lambda. So you have T half is equal to 0.693, then divided by the value of lambda was given to be 0.077. All right, if you divide it, whatever is your value, will give you the answer in seconds. If per seconds is moving up, it will turn to seconds. So that means your half-life is going to be in seconds. But the SI unit of decay constancy per second. So at the end, if you do your calculation well, you have 9 seconds. All right.